Hey everybody, so today's plan is to actually do a little live programming that I can show to both my audio class and my Rust class. And with that, what I really want to do is to put together a little pure Rust demo that doesn't use any external libraries, that creates a WAV file with a sine wave in it. And so to do that, we're going to have to understand a little bit about how to do some basic Rust programming and how to make a sine wave and how to put the sine wave into a WAV file in such a way that we can play it back. So the goal here really is to try to reproduce something like this. I'm going to use the socks utility to actually make a file that contains a sine wave just to play with. So this is the out-of-the-box way of doing it. And then let's play that sine wave and see how it sounds. Well, there's a 3-second sine wave at 1 kilohertz. 1 kilohertz is sort of the standard format that you'll see people use. The other obvious choice would be a 440A, which is sort of the musician's choice. But of course, we're not really musicians so much. We're more computer scientists. So some of us are musicians, but I'm also a computer scientist, so I'm going to go with 1,000. So if I look at that file, I'll see that it's pretty decent sized file. It's 0.5 megabyte, which is a lot for 3 seconds of audio. And if I dump that file, what I'll see is that it doesn't look like much of anything. It's got a bunch of sound data, but it starts with a riff format header and then a wave format header, and the rest of some of that block up to about where this 0F is here is actually the header of the WAV file that describes what's in here. After that, what we have is a bunch of audio samples, and so we're going to try to sort of produce something similar, not necessarily exactly the same, by writing from scratch some Rust code. So let's start with the Rust part. What I'm going to do, I'm in my source directory. Actually, I'm going to go to my homework CS510 Rust. Whoops, boy. I'm going to go here, and then I'm going to go ahead and make a directory for this. We'll call it Rust WAV, for lack of a better name, and we'll cd into that. And now we're going to do cargo init --bin, which will create a nice little template binary file that we can use for doing our wave thing. So we have sort of two tasks here. One is to actually write out a wave header, which means opening a file and writing some header bytes into it that actually describe the PCM format of our sine wave file. And then we need to write a bunch of sine wave data into that file as well, so that we can actually end up with the sine wave in our sine wave file. So let's go ahead and do some of those things. Let's start with this. Well, first of all, there's nothing in here yet. I would suggest now would be a good time to go ahead and git commit this. Always keep your stuff in Git. It's a really good idea. And so there, my initial commit usually contains what is this file going to do. This is no exception. And now let's go ahead and dive into actually rusting a little bit. So there's some things that we're going to have to understand if we're going to make this thing work. And the first thing to understand is sort of how do I deal with files. And to do that, I can look through the Rust documentation. The Rust documentation is fantastic. And I'm going to say Rust stood file, and I'm sorry, I don't know how to actually make the font for the URL bar bigger, but there we are. And there's standard FS file. So how do we create a file and write bytes to it? Hey, look, the first example is exactly the thing we wanted to do. So I'm going to go ahead and take some of this stuff and just use it as stands. Notice that there's something funny going on here with standard IO result. I'm actually going to ignore that part, but let's at least get the headers we need and put them in our program, and now we have the stuff we need to actually do this thing. And then let's look carefully at the example here and see if we can get it to do what we want. So the first thing I want to do is actually make a file. And here we're using Rust's question mark operator to, in the example, we're using Rust's question mark operator to actually mess with that file, but I don't really actually have any interest in doing that. What I want to do is to actually make a WAV file called sine.wave, and I'm going to .unwrap. So this will cause the thing to panic if it can't create the file, which is, you know, different than what we're doing in the example, but that's okay. Now let's go ahead and just see if that much of it actually works. And so let's start with doing that. Cargo run, and we'll see if this compiles and runs. Oh, interesting. Interesting. Unused import. Oh, I see. It's just warning me that I'm not using that, and that I'm not using the file, and the variable doesn't need to be mutable. All of those things are true so far. And so let's look at this thing a little bit, and we should see here, and there's sine.wave. Just like we actually expected it to be there, it is in fact there. And if I look at it, it should be 0 bytes in size. It is. So now we've actually figured out how to create a file, and if you look back at the example, there's a nice example of using the write all thing to write what's called a byte string. This just writes the ASCII bytes, in this case, since it's all ASCII, into the file. You might ask, well, when is the file closed? I don't see a close here. Well, that's the same Rust magic that does freeze. When this file is no longer statically reachable, when the compiler can prove this file is no longer usable, which is when we exit main, then the file will be automatically closed, which is kind of nice. So you can never forget to close a file that's not actually a thing. In this case, it doesn't matter that much since the process is going to exit anyway, but the point is this is the default way in Rust of getting a file closed, is just to let it go away. So the first thing we're going to have to do is build some code to actually make a sine wave. So let's start actually without the WAV file. Let's just start with a sine dot, I don't know, dot PCM file. And let's go ahead and make one of those. And to do that, we're going to go ahead and make a thing that writes bytes of a sine wave into a file. So we're going to have to decide how many bits per sample we want. And for now, at least, I think I'm just going to go with 8 bits per sample because I really don't care that much about the fidelity of this. So let's make a new function. Make sine, and it is going to return a vec of U8s. Now, a vec is the mutable version of an array. It owns its own data, and so this is really just essentially an array of U8 values, U8 being unsigned characters. And well, let's make it I8 because it's going to be more convenient. I'm thinking ahead a little bit to how a WAV file works. Let's make it a U8. So we're going to have to be really careful to sort of offset and scale the sine wave appropriately. So let's make a new vector. Vec : new. We're going to now think a little bit about some things. So we probably need some constants here. We got to decide what we're doing, right? In particular, we've picked a sample format, but now we need to pick a sample rate. So let's declare a constant for the sample rate. Again, I'm thinking ahead a little bit to what the range of sample rates is. I'm going to say this is actually a U16. and it's going to be 44 100 hertz. 44 100 hertz, of course, is the frequency that CD uses, the sample rate in samples per second that CD is used to record. And let's actually allow it to specify a number of seconds. And here we might as well just go ahead and use a U64 because why not? No, sorry, we need a U size because later on we're going to go ahead and push that. So now what we're going to do, and this isn't the perfectly most rustic way to do it, but it's a good way, is we're going to go ahead and just push sine samples onto that buffer to make a buffer full of samples. And what you'll see is the vector automatically grows as we use push to be the size that it needs to be to hold the next sample. So what we're going to do is sort of, oh, and we also have a frequency problem here. So we're going to go ahead and specify that. So now we get to do a little math to figure out what a sine wave is going to look like here. And what the sine wave is going to look like is we want it to, we know what frequency we want. And so if we want it over that period, we want that many per second, right? Then our sinusoid is going to have to vary that many times in a second. Well, the period of a sinusoid is 2 pi, right? And I'm just going to put pi in there right now because I don't care. Oh, right, the frequency probably would be best expressed, honestly, as an F64. So let's do that. And so it's 2 times pi. I should actually look up what the Rust pi mathematics are here. Rust constant pi. F64 constants pi. Okay. So why don't we use that instead? So it's 2 pi times, they're divided by here the number of cycles per second, which is freak. Sorry, what I want to do is the total number of samples, and then I'm going to put a sample count in here, right? So S, so this is the sample counter here. Right. So n6 times sample rate will give us the number of samples. So now we get to play the units game, and the units game here is always exciting. So let's write the outside of the for loop first, like sensible people. The sample that we're going to generate is going to range from sample number 0 up to sample number n6 times sample rate. Right, and so that what that means is that type-wise, maybe that should be a U16 too, so that everything works out. And so now we have exactly the right number of samples that we're going to put out. Now notice that in a real application, you'd probably want to allow a floating point number of seconds, so that would be a thing we could do, but I don't really feel like messing with it right now. And what we're going to say is, let's call that T, that's a better name. What we're going to say is that the sinusoid, we're going to take the sinusoid sampled there, and that's going to be that 2 times F64 consts pi times T divided by, and again, this is kind of the gross way to do it, divided by sample rate as F64. So now that thing is going to give us a sinusoid to start with that's sampled the right way. And we need a let here. And what we're going to do then is we're going to go ahead and I accidentally builded. So what we're going to do then is go ahead and actually take that little sine value and we're going to spit it out. Again, sorry, I'm thinking back. The default, that's fine. So what we're going to have to do is scale that and turn it into a U8 like we want. So this is classic Rust, is I'm just going to scope out that S with the other S. This is actually a super common thing to do in Rust programs, and it looks a little weird if you're used to other languages, but it means that I don't have to keep track of a whole bunch of different variables that have different names. I'm not going to use the first S anymore, so I'll just replace it with the second S. So here what I'm going to do is take that sample value and I'm going to, now notice this will be a number between -1 and 1, and so I want to scale it to be between 0, -0.5 and 1/2. I'm going to add 1/2 to it, so now it's between 0 and 1. So now I have an unsigned value, which is what I wanted in the first place. But of course, I can't stop there. I'm going to have to go ahead and multiply that times to get a number between 0 and 255. So I'm going to multiply it by 255. And then, so now I've got a number between 0 and 255 inclusive, and that's fantastic. That's exactly what I wanted, but of course that's not a U8 yet, and probably the best way to do that is to use F64 floor of that thing, and then turn that into a U8. And then I'm just going to push this onto this buffer, buff.push_s. And when I do that buff.push_s, the size of the vector grows by 1, and off we go. Now I'm going to do a little bit of premature optimization here, just to show how it's done. I'm going to take this, this actual calculation of the number of samples, and I'm going to put it out into a separate variable. Always give separate names for things. And then I'm going to use this with capacity. We know exactly at this point how many things we're going to push into this buffer. So let's just push it in there. Let's make the thing pre-allocate enough space for it. So this push doesn't actually, change the amount of allocated memory. There'll be no reallocations here. All that will happen is it will stick it in the next place in the vector. But the vector tracks the length correctly. If I were to return before this loop finished, that would be okay. And then the last thing I want to do is actually return buff. Well, now I've got a vector full of U8s. Let's go back to our example here of sort of what it is we're trying to do and look at the part where we actually write it out. It looks like there's a write all here that I can use. And there again, it's going to potentially return an error, so I'm going to have to unwrap it or whatever. But in this case, I'm not going to be doing that. I'm going to be saying let buff equal make sine, let's say 3 seconds at there again, 1000 hertz. And now I can just write that buff. Except I can't. I actually have to pass a reference to the buff because that's how this works. And then I'll unwrap because I really want to make sure that I didn't get an error while I was writing. And now I should have a thing that will write the samples of a sine wave into a file. Let's go ahead and cargo build that. And it's like not in sample, in samples. So that's just a dumb typo. That's easy. Oh, right. And it's should be F64 sine. And n samples here should be as U size. Is there some reason n samples isn't a U size? Oh, right, because n seconds wasn't. Right. Yeah, let's do it that way. Let's actually make the number of seconds be a U size. Oh, what the heck. Let's make it BU64. And we'll just go ahead and turn these both to what they need to be. There we go. And now we should be in good shape type-wise, and everything should be good to go, except maybe T here is going to cause us a problem. Ambiguous associated type. So I really needed that stood there. Not sure what's going on there exactly. And yeah, now this is going to have to be T as F64. And notice that this expression's gotten too big now. It's really dumb. So let's break it into pieces and do it that way. We'll just call that W because we need to pick a name. And so now we'll do that. And now let's see if it'll build. Oh, unused variable freak. That is a little odd. I thought we went ahead and multiplied by the frequency. We didn't. We forgot to. Okay, well, that's fine. Oh, right. It should be 2 pi f t. So there we go. And we can get a thing there. Freak. There we go. And now what is it complaining about? See, the thing's very whiny about it. Freak now is an F64. Oh, I see. So I really was right the first time. See, the compiler's very, you know, the typing's a lot pickier than it is in C. There's no automatic promotions. There's no compatibility of anything. It's like, no, make everything all the same type or you're going to be really sorry. And now we should end up with a sine.pcm. See if it looks like it's a reasonable length. It does. Let's actually see if we can play it. This is the SOX play command, which I'm going to use because I want to be able to set some stuff the way we set it when we actually wrote out this file. See, the problem with this is just a bunch of PCM samples. We had a lot of choices we made. We chose to use 8 bits per sample. We chose to use unsigned numbers for the PCM samples. We chose to use 44/100 samples per second. And none of that information was buried in the file. You just have to know how it was created in order to be able to play it back. So we're going to do that. We do know how it was created. We're going to try to play it back and make sure that so far so good we've got a sine wave. Having said that, we are going to go ahead and give some format for the SOX command that actually does that, but then we're going to go ahead and put a wave header on there. And the purpose of the wave header, this is an old Microsoft file format standard, is to record all that information about what kind of PCM samples are in the file, so that later a player can just play it back without, you know, by looking in the file header to see what's going on with it. So let's go ahead and look at how we do this. It looks like the arguments we need are going to be let's actually just use SOX to play this, it looks like. So we need minus B8 because we have 8-bit samples. We need minus R44/100 because we have that. We need minus C1 because we have one channel, right? We haven't written any stereo yet. And let's see if that's enough to get it to play some reasonable way. Let's just try it with sox play. Play minus R 44100 minus B8 minus C1 sine.pca. Oh, right. Right. We need a format header. And I think that's the minus F. And then we need to tell it that it's U8. Nope. I don't remember what the argument is for the format header. Audio file formats. How do you give it the format options? Maybe it's just minus U8, but I kind of don't think it is. Format. It's been a while since I've used sox, and you always have to go figure this stuff out. Right. Minus T. And there we are. We've got our sine wave coming out. It sounded a little rattly to me, but I think it's actually doing what it's supposed to be doing. So that might just be because it's way too loud. We might want to apply a volume modifier to it. This is a maximum amplitude sine wave. And there's two ways we could do that volume modifier. One is we could change our Rust program to be softer. The other one is that we could just have the volume factor argument so that we play it at some reasonable volume. There we go. But it's a little buzzy. So why do we think it's a little buzzy? I mean, the other one didn't sound so bad. When we were just playing it with sox itself, it sounded not buzzy at all. Well, we've now got 8 bits per sample, right? We've got quantization noise. So what you're hearing here probably is that you just don't have enough resolution to get a smooth sine wave at 8 bits per sample. But on the other hand, the file format's small. That's kind of nice. Let's go back to the original thing where we actually used the synth to play it. And let's actually just play directly a thing like that. Let's actually make our wave file, as my point, actually be 8 bits per sample. So let's do minus T U8 minus R 44100 minus what was the other thing? C1 minus B8. Actually, I think if you have minus TU8, you should be good. And now let's play that. Whoops. What? Oh, right, not minus TU8. Oh, I see. Where's my synth command? I don't want minus TU8, I want a wave file. So, but I wanted it to be an 8-bit. How is the signedness specified? There's a way to specify whether it's signed or unsigned. I need to find that. This is the play arguments. No, it's the sox arguments. Minus encoding signed integer. Minus E signed integer. I gotcha. Or unsigned integer. There we go. Yep, and it sounds kind of terrible there too. So it's pretty clear that what we've got is pretty much what we're supposed to have. That's kind of nice. Let's see if the file sizes are comparable. They are. They are. So it looks like we're in good shape. So what do we do now? What's the next thing we always do in this situation? got sine wave working as PCM. We commit. Never ever forget to commit your work as you go. So cool, we've got a thing that makes a sine. The hard part in some abstract sense is done, but of course what I want is a sine WAV file. The sine.pcm was a cheat to just get us up and running. What I really want to do here is to actually write out a wave file header before I do that. And so I'm going to rename this, I'm going to call this sine buff. And I'm going to also make a thing for the header, and I'll stick the sine buff on the end is what I think I'm going to do. Now, if I'm really being efficient here, if I really cared about efficiency, what I would do is make the header, and then I would stick the actual sine wave on the end of that by doing pushes, and everything would be really super efficient and cool. The problem with that is that it turns out that in the wave file format, I need to know how long in samples the sine wave is before I, so that I know how long the chunk is, blah, blah. There's a whole bunch of I need to know how long this is. And so we're going to do this a less efficient way that lets us make it easier. Let me be really clear. All of this is to demonstrate Rust programming and making sounds. There's absolutely nothing about this that's about doing it the best possible way. If I were doing this for real, I'd be using Rust crates, at least for byte endianness and writing out files. We'll see the problems there in a minute, but I would probably also just use a Rust crate that was a wave file crate. There's a very nice one called RiffWave that you could absolutely use as a library to actually do most of the work of the wave part of this thing. So there's that. But for our purposes, I kind of want to do everything from scratch. And so I'm going to go ahead and make a another function, fun make wave header, make wave, I guess we'll call it. And that's going to take sort of a U size representing how long the actual sine wave is, and so I'll have to actually call that second. And so what I'm going to do then is I'm going to go ahead and say n samples is U size. That's going to be our thing, and that's also going to return a U8 that vector of U8s that represents the actual header of the file that we're going to do. So now we've got ourselves the empty header, and I'm realizing now that I forgot to correct this to match. So what I'm going to do now is make the sine buffer. I'm going to go ahead and let wav buff equal make wav sin buff.len, because this is an buffer full of U8s, so actually the size is exactly what you want it to be. And now we're going to sit there and try to figure out how to push some bytes into this thing. So let's go ahead and look a little bit at what the WAV file format itself looks like. It just so happens that I have cheated a little to make things faster and made this go ahead. And here's somebody's description. This is the one from MMSP from McGill. Here's somebody's description of the WAV audio file format specification. And there's a bunch of references to Microsoft documents and EBU documents and et cetera, et cetera. Let's go ahead and read this document and try to understand what it's telling us. Apparently a WAV file starts with a 4-byte string that contains the ASCII characters RIFF. That's the first thing we're supposed to have. And then we're going to have a chunk size, which contains the the chunk size is the size of the next chunk in the file, and in this case it's going to be 4 bytes for the chunk header, which is wave, and then followed by n bytes of the actual stuff. And so the format chunk here is going to be, again, a nested chunk, nested inside the wave chunk. And so what we're going to do here is we're going to go ahead and look at all these things. Here's the four, so we have however many bytes total this is. We're going to have all of those. And these things contain what? They contain a chunk ID again, the size of the chunk, which is to say how many bytes does the chunk header itself have, because this is the format chunk. And then we're going to go ahead and have format code. And to find out what that means, we look down here and see that we're going to be doing WAV format PCM. So the format code should be the code 1. We have one channel, so we're going to have one channel. We're going to have the sample rate in samples per second is 44,100. The data rate, which is the same as the sample rate, this is in bytes per second, and so this will also be 44,100 because they're the same. We don't need any alignment of the data. 1 is perfectly fine. If you're using 2-byte samples or 4-byte samples, you're supposed to align the samples to that as well. So this is the block size in bytes. Sorry, that's what it is. So our block size is 1. And our bits per sample is 8. And our chunk block size is the size of the extension. That'll be 0 for us. And then this is all extension data that we don't actually have, so we can ignore it. So I think we understand how to stick a wave header on this. It's just going to be writing out a lot of bytes. Now, we're going to have to go ahead and figure out how to do that in our Rust code. So let's go ahead back and do that. Let's start sticking some things on there. We're going to go ahead and say that this chunk ID, that first chunk ID is going to be riff, right? That's what we start with. So we're going to go ahead and say let mute buff equals, we're going to basically copy and paste code from here, except this time we don't really know what capacity this thing wants to have. It wants to have however many it wants to have. So let's just save that :new. You really don't have to worry about these efficiency things if it isn't easy to do. And so now the first thing I'm going to do is buff.extend, which as it turns out sticks stuff onto the end of a buffer, and I'm going to use the byte string trick again. So now I've stuck the 4 characters RIFF onto this buffer, which is how I was supposed to start. I'm in good shape so far. So the next thing I'm going to do is add the size of the chunk. So I'm supposed to have a 4-byte field that indicates the size of the wave chunk. Well, I know how big that is. That's 4 plus the length of the wave chunk, and the length of the wave chunk is the length of the format thing. So that's chunk size 16. And then, so I'm up to 20, and then I actually have to have the data on the end, so it's 20 plus n samples, I think. So I need to now, I need a way to make a 4-byte, a 32-bit number as a bunch of bytes that I can stick onto the end of my byte vector. And so I'm going to do this the dumbest possible way. This is not what you would do. Like I say, you'd use the byte endian crate normally in Rust to actually do this conversion for you. But in this case, we're trying to do things the dumb way. So we're going to have make U32, and it's going to take a value, which is a U32, and it's going to return an array of 4 U8s. So I can do that. Let mute b equals 0 U8 semicolon 4. So notice that I'm now initializing this with 0 bytes, that's kind of gross, but there's no way to not initialize an array in Rust, or at least no sensible people way. When it's created, it has to be initialized at that point so that you don't have memory issues with uninitialized memory. So we're just going to put some zeros in there, and then we're going to write over them as needed. And now the point is, what endianness is a WAV file number supposed to be? Let's go back and look that up as well. Little endian, file boundary is little endian. That makes sense. It's a Microsoft standard, and so it's going to work well with Intel. It's a Wintel standard. So I'm supposed to write the least significant byte first. That's cool. So I'm going to say b sub 0 equals v and as u8, but really I should be looping here, so let's do the obvious looping thing. Let's go ahead and do that. B sub I equals v shift right I, and 0xff is u8, and then I'll just return b, and now I've got a way to make a u32. So buff.extend make u32, whoops, buff.extend b make u32, and there again I'm going to have to watch out for ampersands here, and the number I'm going to use, I think I said, was 20 plus the number of samples as u32, and now I've written out the length. Well, that was painful and gross, but there we are. We've got the riff header mostly written out. So now let's go ahead and start writing the wave header out. The riff header's written out. We really need to write out the wave header. Well, we already know how to do that. Wave. So if the chunk is called a wave, why is the file called a WAV file? Well, because Microsoft in the old days only allowed 3-character file extensions, and it still kind of does. So it's kind of gross. And now I'm supposed to stick on a format chunk, and we already know how big the format chunk is supposed to be. It's supposed to be 16 bytes. So let's do that. Is that right? 16 something, 16 bytes, I guess. 4, 8, 10, 12, 16. Oh, interesting. Right. So the rest of this stuff is actually part of an optional extension too. So we don't have much more to write. We have to write out the format chunk ID. So we know that trick. That trick is familiar to us. All right. Now we need to write out the format code, no, the chunk size, which in this case is 16. And that's supposed to be a 4-byte value again. So now we know how to do that. In this case, we're going to write the chunk size of 16 out. And now we've got the wave format chunk started. The next thing we're supposed to write out is the number of the format code. We said the format code was supposed to be 1, but oh, it's a 16-bit value this time. So we'll go ahead and build this obvious thing. And this is terrible copy-paste coding. I really should parameterize this somehow, but it's really hard to, because again, the size of an array is encoded in its type, and the type here needs to be different. So I really am going to be sort of stuck with this ugliness. And here this should be a 2. I think that's all the endianness games I need to play. This line looks fine. This line looks fine. So All right, that looks plausible. And so now, having written the format code, I'm supposed to write the number of channels, which is a 2-byte value. Well, that's also a 1. So we write another 1. We should probably start commenting these. And this was format code PCM. And was it unsigned or signed? I don't think it specifies that here. It's just format code WAV format PCM. Oh, right. That's one of the dirty little secrets of WAV that you've just got to know. It turns out that for Microsoft's WAV file format, byte-sized samples are unsigned. 16 and 32 byte 2 and 4 byte 16 and 32-bit samples, which are the other sizes that are supported for WAV files, are signed. Yay, magic! We love magic. But in this case, the magic works in our favor. It just makes things a little more convenient for you writing out and stuff. And this last thing was number of channels. And then we're going to have to write out some other things. Number of samples per second. And I think that's the last thing, and that's a 4-bit number. So we go ahead and write out sample rate here. And what format did I actually make sample rate be up here? I think I really want that to be a U32. I was trying to look ahead and I failed. So we got all kinds of types floating around here. This is a great example of Rust's sort of painful insistence on all the types being the same, sort of getting in our way, because it means that we have to keep remembering to do these type conversions. But on the other hand, it fails safe. You're not likely to get a conversion you didn't want. You're just not likely to get a conversion you did want unless you actually write it down. And there are worse things. So I kind of feel like our header is done now. So let's just return it. And now we're just going to go ahead and write these things out, right? I'm going to write the WAV header. And then I'm going to write the sine header that actually contains the data. And let's see if this builds. I'm almost certain the answer is no, because, you know, welcome to the new age. Oh, right. I typoed there. There's going to be typos at this point because I'm getting tired. It's been a while. Hey, look at that. Compiled and ran on the first try. Let's see what it actually does when we run it. Oh, did I remember to change the... I did remember to change the extension. So we got a thing that builds. Whoa, okay. Is this the current sine.wave? It is. It's midnight and here we are. So, and it looks like it has the right size. That one actually has the extended header in it that we made with socks. That's okay. We don't need the extended header. This header should be enough. Let's see what happens. Oh, don't understand WAV size. So that's too bad. Let's see what PA play says when I try to do that. Failed to open audio file. So we've got a formatting problem. And let's now look and see if we can try to figure out what's going on. And probably the easiest way to do that is so let's go look at those files. Here's the actual real one. Oh, interesting. So we can sort of just glancing at the ASCII see that we have this funny, weird thing going on here. So here's the riff header. And in our thing, it's pretty clear that we've somehow really screwed up. Oh. So this chunk is supposed to only contain the size, apparently. Notice what we've got. We've got riff, and then we've got this number, which is, in this case, interesting. You'll notice that things more or less line up, and they're more or less the same, but in this case, we've got something really funny going on here. So let's go back to our thing and see what the deal is. Do I need a separate data chunk? Maybe I do. Oh. I'll compress non-PCM formats. I don't care. Oh yeah, there needs to be a data chunk. So we weren't done writing the file yet. It's like, I don't quite understand what you've done here. So let's just go back, assume that we got the header more or less right, and let's go ahead and write a data chunk, which is what I didn't remember that we needed to do. So it turns out that I did this wrong. So let's make this just be 20, which is the correct answer pretty clearly for this chunk. No, it isn't. What I need to do is just follow this with a data chunk. So let's do that, and at this point we need to have a data chunk. So we stick data in here, and this pretty clearly is wave chunk, format chunk, and then we have this data chunk. You know, it's important as you go when writing programs to keep this stuff clear and formatted so you can figure out what's going on. And the chunk size here is going to be the size of the number of samples, I think. N is the number of samples or the number of bytes. Right. And then the pad byte is either 0 or 1. It's there's no pad byte here because thing. So because there can't be padding on a 1-bit value, so we're going to be good. So what we now do is this again. Now, did I get the wave chunk right? Let's go back up to the top and look at the wave chunk itself. Maybe I'm supposed to have another size in here that I didn't have. Maybe I misunderstood how this works. This is pretty common. Oh. Oh. Right. So this is actually right. Let's go ahead and get this data chunk set up and call it good to go here. So I think that's this again. The data chunk contains is a 4-byte field. It's the chunk size. So after we write data, we're supposed to write make U32 n samples is U32, and that may give us a better answer. Let's try running it now. We'll build it. Does it compile? Oh, right. I forgot to return the data, the buffer. That would be probably helpful. There we go. Nope. Don't understand wave size. PA play tells us failed to open audio file. So we're back to where we were before. All right. Don't understand .wav size. Okay. So we're still shy of how big we're supposed to be. So now we got to do some careful sort of auditing of this to understand what's going on. First of all, these are supposed to be little endian, or did we do the little endian right? We took the low byte and stuck it on the left, and then the next lowest byte and stuck it after that. I sort of feel like this is little endian, so I think that's actually all right. Let's stare carefully. The U32 one is also correct. So I'm sort of happy with the make U32 and make U16. So the question is, where did we screw up with the headers? So let's then again look at this thing over here. Socks. Us. So riff, those are the same. Here's where we first disagree about what's going on. This one is should be the number of samples plus the size of the header, but our headers are a little different. For us, it's 70E0. For them, it's 04FF. This 7 looks really suspiciously large. So something weird has happened here. Did I get wrong? Oh, right. No. Sorry. This is the overall size. 9C. Yeah, this is a giant chunk. Isn't this the next thing? This is a make U32, the number of samples. That's a lot of samples. I sort of don't believe there are that many samples. So how did we go that wrong? Let's go back up and look at the WAV chunk. Yeah, this should say riff and then the chunk size, and the chunk size should be a 4-byte number, and it certainly shouldn't be that big. That's sort of insane. So something's gone horribly wrong here. Let's go look at our code again. The riff chunk. Huh. All right, let's look at the vector extend method. I must have misremembered how it works. Rust stud vec extend. So this is an iterator method, this extend thing. This probably isn't what I wanted. I'm probably using the wrong method here and getting myself in trouble. Extend from slice is what I actually wanted here. Yes, this. There we go. Let's see if that works better. Let's try it now. Yep, nope. So let's do the HD thing again. Let's go find us. Yes, reread from disk, and let's see what we got. 9C3870E0. Huh. I sort of feel like that can't possibly be right. This one is a much more sensible 000204F0. This is, quite a few thousand bytes, but it's not anything insane, people. It's actually just about the right size. This size is not even wrong. So what did I do? Riff, and then 20 plus the number of samples as U32. And the number of samples here is a U size, which it shouldn't matter. I should be able to downshift that to a U32. Is N samples just wrong? No, sinebuff.len. That should be fine. Huh. So we got some kind of bug here. And probably the easiest way to debug this, we could debug it with GDB, but probably the easiest way to debug it here is to just go ahead and take this. And do that. And then let's go ahead and print this here. Println bang. Let's make sure we're seeing what we think we're seeing here. I kind of think we must be :0x or :x question mark r size. So let's do that. Sure enough, 9C3870E0. Why would that be? So the number of samples is wrong, maybe? Let's see if we've got the wrong number of samples. No, the number of samples looks right. So somehow I've screwed up my conversion routine. It's not spitting out the buffer I thought it would do. So let's look at this closely here. Yep, there's the problem right there. Probably want to shift by a byte at a time, not a bit at a time. And so welcome to the wonderful world of debugging. This should be a lot more happier. Yep, that's what I did. Okay, there. And now I get 204cc, which actually looks very, very plausible. And so now let's play star.wav. Could not find data chunk. All right, so we've got past our first little dumb adventure, which is that you probably got to be really careful about these dumb conversion routines. Like I say, if we had used a Rust crate for this, we wouldn't have had this problem. So we only have a little more to go here. We're almost done. We're in the home stretch. Let's look carefully at why it isn't finding the data chunk. There's a format chunk, and the size of the format chunk was set to 16, and I think that's right. We have, no, 2, 4, 8. Yeah, we somehow screwed up here. 12, so we're missing a field. That's all that's going on here, and that's easy to fix. Let's go ahead and look and see what field we forgot to put in there. The format chunk should have, the format code is 2 bytes. Oh, the chunk size, then the format code. Chunk ID, chunk size, format code, number of channels, samples per second. So that should be 4, 8, 12. Oh, I see. The data rate should actually be part of this, the included thing. 2. And I'm not sure if the chunk size is counted. There's 4, 8, 12, 16. Yeah, so I need all 16 of those bytes. So we need to write out the data rate, and we need to write out the data block size. The data block size is 1. The data rate is the same as the sample rate. So let's do that. That comment's wrong in any case. Sample rate. And then we need another thing here, right? What did we miss? Format code in PCM. Let's see. Oh, this is fiddly. format code and number of channels. That's that. Oh, right. And then the data block size and bits per sample. Data rate, data block size, which is 1, and the bits per sample, which is 8. Both those are shorts. Okay, fine. Data block size. What even is that? Oh, that's the alignment value. And then the bits per sample, that's essentially the frame size, I think. And this is bits per sample, which should be 8. So this tells us of those samples that are in there. No, we just forgot to put bits per sample. Okay, that's fine. Okay. And yeah, this is the number that can be either 8, 16, or 32, depending. So let's try to run that now. We should get that debugging out of there. Listen to that. We've done it, folks. We've written a WAV file. So let's do our cleanup. Where are those debugging prints? I really don't think I need them ever again now that I've solved my problem, so I'm just going to make them go away. And now I'm going to do the last thing that you do in this, well, the next to the last thing, which is git commit -am change to write WAV file instead of raw PCM. And there we are. We've got ourselves a Git repo with our little thing in it. Now there's still things that I should probably do here before I actually call this done. One is that this file contains exactly 0 comments other than those ones I just put in. I should really Rust doc this file up with really extensive comments that say things about authorship, etc., etc. I should probably put a README in this directory that actually says what this thing is and who wrote it and what the license is and some stuff like that. I should probably put a license file in this, and then I should push it all up to GitHub or GitLab so that people can play with it. The other thing that I should do, because there's always more things, is, well, if I do all those things, if I comment it out adequately, add a README, add a license file, and push it up to GitHub, then it's probably about as good as I can get. If I were going to do future work things, even more than I've done in this hour and a half that we spent playing with this, it would be to go ahead and split out the part that actually writes the buffer of samples into a separate library crate, and that way I could swap out the part that makes a sinusoid, and I could now have a little self-made library. The other thing I do if I were doing it for real is, like I say, I'd just get rid of all this hand-built stuff that was there mostly as an exercise to see how things worked under the hood, and replace it with use of standard Rust libraries for doing all these things, because really doing this ourselves is kind of nutso. But that is how PCM works, and that is how you write a Rust program that produces a WAV file. I hope this was useful. You know where to find me if you have questions or comments. Thanks.